Every electrical system, from a pocket flashlight to an industrial power grid, relies on three interacting forces. Resistance is the physical opposition to energy. Current is the actual flow of charge, and voltage is the electrical pressure waiting to be released, much like the immense physical pressure of water trapped behind a dam. For over a century, engineering diagrams have shown this current flowing from positive to negative. That convention is actually physically backward. The real charge carriers, electrons, flow from the negative terminal to the positive one. We keep the old diagrams simply because correcting billions of schematics worldwide would be an administrative nightmare. There is also a widespread misunderstanding about exactly which of these forces causes bodily harm. High voltage warning signs suggest that voltage is the lethal element. In reality, voltage is just the pressure. It's the current, the actual volume of moving charge, that does the damage. A current of just 100 milliamps, or 1/10 of a single amp, is enough to cause severe physiological harm. To put that in perspective, a standard smartphone charger can deliver up to 3 amps. That is more than enough current to be dangerous. The reason your phone charger is safe is that it only operates at 5 volts. 5 volts simply does not provide enough electrical pressure to push that current through the natural resistance of human skin. This mathematical relationship between pressure, flow, and resistance governs how water transitions from a simple fluid into a functioning part of an electrical circuit. Pure, perfectly deionized water has extremely high resistance. It is essentially an electrical insulator. But the water that comes out of a standard kitchen faucet is entirely different. It contains dissolved mineral salts, which break down into electrically charged ions, turning the liquid into a ready conductor. Engineers measure this ionic conductivity using a specific metric, microsiemens per centimeter. This unit tells us how easily current passes through a fluid. If you look closely at the specifications for an industrial electrode boiler, you'll see a requirement right on the casing. The hardware relies entirely on the water possessing a conductivity around 200 microsiemens per centimeter. If you fill the system with distilled water, the conductivity drops to near zero and the system stalls. If you use extremely hard, mineral-rich well water, the conductivity spikes too high, drawing excess current and tripping the circuit breakers. These dissolved mineral salts turn common tap water into the primary electrical conductor required for the boiler to operate. To see how this works, we have to look inside the hardware. From the outside, the unit is a heavy, compact industrial cylinder. At the base, standard electrical connections feed directly into a set of electrode rods that mount securely up into the main chamber. But when you look directly into that chamber, there is no traditional heating element. There is no tightly wound resistive coil and no sealed tube designed to glow red hot. There are only smooth, solid metal pillars. A physical cutaway of an older unit proves the point. The internal volume contains the outer wall and the central rod, with completely empty space between them. There are no hidden heat-generating components anywhere inside the casing. The device itself is completely incomplete. It is literally half of an open electrical circuit, waiting for a very specific fluid to arrive and cleanly bridge the physical gap between the metals. Let's examine the internal layout of this single-phase chamber to see how heat is actually generated without a coil. When alternating current is applied to the electrodes, it changes directions dozens of times per second. This rapid oscillation forces the suspended mineral ions in the water to violently crash back and forth. This creates molecular-level friction. In physics, this is called Joule heating, energy dissipating as thermal heat wherever an electrical current overcomes resistance. Because this friction occurs between the ions suspended in the liquid itself, the water acts as its own heat source. The energy is dissipated uniformly throughout the entire volume of the fluid at exactly the same time. This creates an automatic, unbreakable safety mechanism. In a traditional electric heater, if the tank springs a leak and drains, the dry metal coil will rapidly overheat, melt, or start a fire. Here, if the water drains out, the conductive medium disappears. The circuit is physically broken. The system stops drawing power instantly, with zero reliance on digital sensors, thermostats, or mechanical relays. By removing the physical heating element entirely, the fundamental physics of the water itself becomes the ultimate failsafe. Let's watch the complete operational cycle, starting from a cold, dormant state. Cold tap water is introduced into the lower inlet of the casing, quickly filling the empty void surrounding the central electrode rod. The moment the water bridges the gap, the circuit closes. Current passes through the fluid, the ions oscillate, and the water immediately begins generating thermal energy as it is pushed upward through the chamber. A continuous, uniform temperature shift takes hold inside the casing. Cold fluid constantly arises at the bottom, acts as a resistor to generate heat, and exits the top at target temperature. There is no energy loss transferring heat from a glowing metal element through a protective casing and into a liquid. The fluid acts simultaneously as the electrical conductor, the precise resistor, and the final thermal output. Because the fluid dictates the power, the system's output can be manually calibrated. If a building is in an area with very soft water, an installer can literally add a pinch of table salt to the system to increase the ion count, lower the resistance, and boost the heating power. If the local water is too hard, they dilute it with distilled water to bring the power draw back down. This chart shows safe operating conductivity, holding steady, and then what happens when standard heating antifreeze is added to the pipes. Most automotive and domestic antifreeze compounds are highly conductive. Introducing them causes the fluid's conductivity to spike violently, up to 20 times the safe limit. The resistance drops to near zero, creating a massive current surge that will instantly trip the building's breakers or permanently destroy the internal wiring. Maintaining the water's conductivity within the specified 200 to 300 microsiemens range ensures the system operates with the intended balance of voltage, resistance, and current.